Greetings everyone, and welcome to some very fun elastic collision examples. Now, before we do any elastic collision examples here, let's remember that an elastic collision occurs when both momentum, which is always conserved, and kinetic energy is also conserved. And, momentum is conserved in any closed and isolated system, and kinetic energy is rarely conserved. That basically means that there's no energy dissipated during the collision, and that's not a very typical thing. So elasticity is never something that you would assume. Right? You would never assume a collision is elastic. You either need to be told that it's an elastic collision, or you need some evidence, like the initial kinetic energy and the final kinetic energy are the same. Right? But in the examples we are going to do today, they are all going to be relatively elastic collisions. So as you read number one here, we have two balls, a 35 kilogram and a 25 kilogram, heading towards one another. The 35 kilogram is moving to the right at 15 meters per second, and the 25 kilogram ball is moving to the left at 9.0 meters per second. Well, we don't need to do basic principles. If you watched the previous presentation, then you know that we have these very nice one-dimensional elastic collision equations. If we call this object 1 and this object 2, then the final velocity of object 1, the velocity after the collision, would be equal to m1 minus m2 over m1 plus m2 times v1i plus 2m2 over m1 plus m2 times v2i. And basically, we just need to plug everything in and be careful about where we plug things. Also remember that these are vector velocities. Why is that important? Because since they're traveling in opposite directions, if we define the 15 meters per second as a positive velocity, then the 9 meters per second must be a negative. Notice here that as long as our mass is in the same units, it really doesn't matter what those units are, because they're all going to cancel out. And so we'll be left with a final velocity for this 35 kilogram ball of negative 5.0 meters per second. That means that after the collision, this ball will end up going back to the left, so it's going to rebound off of the first ball. That's something that's hard to predict. It really depends on the relative velocities and masses of the objects, and so this is where the equations can really, you solve the equation and it can tell you what's going to happen in the collision. Well, that's just the final velocity of the first ball. If we use the other elastic one-dimensional equation that we derived the other day, we can find the final velocity of the second ball. Plug all the numbers in, again being careful that the initial velocity of object 2 is a negative 9.0 meters per second, and we get a final velocity for the second ball of 19 meters per second. And since it's positive, that means that the second ball will move to the right. So the first ball ends up bouncing off and going to the left, the second ball ends up bouncing off and going to the right. Again, kind of hard to predict without actually running the equations. So you can see that if you know these two equations, one-dimensional elastic collisions are really pretty simple. You have two unknowns that you can have rather than just one, because it's an elastic collision, and it's really just plug the numbers in and find your answers, being careful with the vector aspects. Now, we could do example 2 here the exact same way and use the canned equations, but I know that sometimes you might have a hard time memorizing them because they're kind of big. And so I want to show you kind of some tricks, if you will. And by tricks, I don't mean bad things. I mean tricks like tricks of the trade here that you can use to see how to do these problems and kind of shorten them up from the way that we derived the very general one-dimensional elastic collision equations. So here we have a 4 kilogram object moving at v1i, and we have an 8 kilogram object stationary. So that makes it a little simpler than the ones that we were looking at in the previous example. Now, I'm going to call the mass of the first object m, which means the mass of the second object would be 2m. Since this is an elastic collision, again, never something you assume, but it says it is in the problem, that means that two things are conserved: kinetic energy and momentum. So if we start out by looking at the conservation of kinetic energy, all right, the initial kinetic energy has to equal the final kinetic energy. The initial kinetic energy is the kinetic energy of the 4 kilogram block, since it's the only one, and I'm going to call that 1. Right? So 1/2 m of v1i squared. The final kinetic energy is the sum of the kinetic energy of the two objects. And again, we don't know what their final speeds are at this point. So we have two unknowns in this equation. But before we're done with it, let's simplify a bit. The 1/2s cancel. The m's cancel. And so we get v1i squared equals v1f squared plus 2 v2f squared. A little simpler than the ones we did in the general case. But we still end up with an equation here that has two unknowns. However, we also know that momentum is conserved. It means the initial momentum of the system is equal to the final momentum of the system. The initial momentum of the system is simply the momentum of the 4 kilogram block, since it's the only one moving, which would be its mass times its initial velocity. The final momentum is the sum of the momenta of the two blocks, m times v1f plus 2m times v2f. Notice here again 2m because it's twice the mass. The m's cancel, and we get a second equation. This one even simpler, but still this equation has two unknowns. But now notice we have a system of two equations and two unknowns. And in this case, because so many things cancel, the masses were multiples of one another, one of the objects was at rest, and we can probably solve this very straightforward kind of algebra, and then we don't need to know the one-dimensional elastic collision equations, although again, if you know them, you could do this problem in just a couple of steps. So, system of two equations with two unknowns. The way to solve that, we solve one of the equations here for one of the unknowns, and then we substitute it back into the other equation, like so. And we now have an equation that only has one unknown, v2f. Although we're going to have to do some algebra here in order to find it. So here are the steps. Feel free to use the pause button. We square the term on the right-hand side, FOIL it out if you will. We get v1i squared equals v1i squared minus 4 v1i v2f plus 4 v2f squared plus 2 of v2f squared. Notice that the v1i squareds on both sides will cancel. And we have two like terms over here, so we add them together. And we get 0 equals negative v1i v2f plus 6 v2f squared. Notice we have a v2f in both terms. Since we have a 0 over here, we can divide through and cancel one of them out. Or if you want to get a little more technical with your algebra, you could factor out the v2f, and that means v2f is either 0 or these things are 0. So one way or the other with the algebra. And now we just need to solve for v2f. Add the v1i to the left-hand side and divide by 6, and you get v2f is 2/3 v1i. Now, at this point, if we want to get really crafty, and use symbols, we could plug this back in, but, this is a numerical problem. So I'm going to plug in what I know is v1i, 6.0 meters per second. And that gives us a nice round 4.0 meters per second for v2f. So that means the second object here, after the collision, ends up moving to the right, because it's positive, at 4.0 meters per second. Here's the equation we had on the other screen. Our conservation of momentum equation solved for v1f. So if we plug v2f in there, and we plug in v1i, 6 minus 2 times 4 is, of course, negative 2.0 meters per second. So the first object rebounds and moves to the left at 2.0 meters per second. And again, it's nice to see that these equations, that you can really do the elastic collisions symbolically if you wish, when you have these kinds of problems, which are more typical ones that they ask on an AP kind of test, where masses are either equal or they're simple multiples, and maybe one isn't moving, or velocities are the same initially, or there's all sorts of different things that they can do to make the math a little easier for you if it was, say, a multiple choice kind of problem on an AP test. Again, if you have those two big one-dimensional elastic collision equations that we used in example 1, you could find these answers just by plugging all the numbers in, one way or the other. Last example, you'll see this is a two-dimensional example. And we're talking here about billiard balls, which are, pool balls, which are relatively elastic. So we're going to assume this is an elastic collision. Now, they're not truly elastic. You can obviously hear them when they hit. There's also going to be some thermal energy stored during the collision. Right? They're going to warm up a bit. But because billiard balls are pretty spherical and they are pretty hard, they're going to end up being a pretty close to elastic collision. So this wouldn't be a bad approximation of what's going to happen here. So we know that the first billiard ball is moving 10 meters per second, and then it runs into a second billiard ball, and that first ball then goes off to flex at a 40-degree angle, and the second one then would, of course, have to go down here. So what we don't know are the two final velocities. But really, we have three things we don't know if we're going to find the final velocities. We don't know the speed of the first billiard ball. We do know its direction, 40 degrees. But we know neither the speed nor the direction of the second ball. So this is three unknowns in this case. But again, being a little smart with what we do here, we're going to be able to figure these things out. We could set up three equations with three unknowns, but I'm going to show you a little faster way of doing this here. First of all, we know that this is an elastic collision. It's a collision, so as long as it's closed and isolated, we know that momentum is conserved. The initial momentum is simply the momentum of the first ball. The final momentum is the vector sum of the momenta of the two billiard balls after the collision. Now, this equation looks simple, but realize that this equation is actually a two-dimensional vector equation because these two billiard balls go off in two different directions here. So this isn't, regular algebra. This is vector algebra. And so in order to see what this equation actually means, it would be good perhaps to draw a vector diagram. We certainly know how to add two vectors together. To draw two vectors head to tail, you draw one vector. So there's P1F at a 40-degree angle, as in the original diagram. And then we draw the second vector head to tail. So we'd start it here and draw here. So here's P2F at an angle as yet unknown theta 2. P1I is the resultant. It's the net effect of adding these two vectors together. And the resultant always goes from the tail of the first to the head of the last. So there's P1I. You notice here we have a vector diagram. But we're not quite sure what the angles are inside, other than this 40. However, this is an elastic collision, or at least a nearly elastic collision. And that means kinetic energy is also conserved. Oh, by the way, theta 2 is the angle down here as well, because this and this are two parallel lines cut by a transversal, so alternate interior angles are congruent. So we also have conservation of kinetic energy. Initially, the only thing that has kinetic energy is the first billiard ball. And then the final kinetic energy is the sum of the kinetic energies of the two billiard balls. And this is not a vector equation, because energy is a scalar. It's an amount of ability to produce change. Well, the 1/2 certainly cancel. And what is true about the mass of billiard balls? Of course, they are the same. And since their masses are the same, the masses cancel. Look what we have left now. We find that the initial velocity squared of the first billiard ball is equal to the sum of the squares of the speeds of the two billiard balls. Well, hopefully that's making some bells go off in your head, because that's only going to be true. The sum of the squares of two sides equals the square of the hypotenuse if this is a right angle. Right angle right there. It's the only way this can be true. So that means that this angle in between the two vectors has to be a right angle, and therefore theta 2 is 50 degrees, or in our counterclockwise from zero notation, it's negative 50 degrees. You could also call it 310, but I like negative 50. Now, this is an important result for you to remember, okay? Because if you remember the proof for this result, you don't have to reprove it. And so in an elastic collision problem like this, as you might see on a test, I've certainly seen this pop up from time to time on AP tests, problems quite a bit like this, you can immediately know what the angle is with really out doing any math at all, as long as you remember the proof that we did here. Well, what's nice now is that if this is 50 degrees, which makes this a right angle, this is then a vector diagram in the shape of a right triangle. And so we don't have to do any complex trig here. We can just do right triangle trig. So we can take, for example, the cosine of 40 degrees is the adjacent side, P1F, over the hypotenuse, P1I. Each momentum is mass times velocity. The masses cancel. Solve for the speed of the first object. We know that the speed originally of the first object was 10 meters per second. So 10 meters per second cosine 40 degrees is 7.7 meters per second. And if we want to have a velocity at the end, we need to add a direction. The direction's right in the diagram. So the first billiard ball deflects at 7.7 meters per second at 40 degrees. Little right triangle trig. Likewise, we can find P2F by using a sine function. Sine of 40 is opposite over hypotenuse. Each momentum is mass times velocity. Masses cancel. Solve. Again, v1I is 10 meters per second. And you get 6.4 meters per second at negative 50 degrees. Again, this squared equals this squared plus v1f squared. And so it's a right triangle. Kind of a cool way to solve the problem. Really reduces down the algebra and trig that you have to do. But you have to recognize that because it's an elastic collision, and this is only going to be true for elastic collisions, that you're going to get this 90-degree angle. If you've got a pool table or you get around a pool table, try this sometime. Now you got to be a little careful here. We're not talking, there's no English on these balls, so these balls aren't spinning. Otherwise that makes things way more complex. Right? So if you just basically hit the ball flat, right, and you watch the angles, okay, you'll see the 90 degrees. When I was in college, my friends and fraternity brothers used to complain that I knew all the angles when we'd play pool, and that was true. I theoretically knew where the billiard balls would go when I hit the ball. That didn't always mean that I could win, but at least theoretically I understood how they bounced off one another. And now, so do you. Hope you enjoyed elastic collision examples, and this, hopefully, if you've watched this before you've gone to class, this should prepare you for the very next worksheet.